Hello and welcome back to Gen Chem with Dr. J. I'm Dr. Janita Pritchett, and on this channel we cover all things Gen Chem related. On this video, I'm going to be covering bomb calorimetry and how to do the calculations associated with it. Let's get started. One of the ways that we go about measuring the internal energy of a system is using a process known as calorimetry. And specifically, we're doing this at constant volume. So when we're measuring something at constant volume, that means that the overall work that's being done on the system is actually equivalent to zero. The reason we can say that is because work is equal to negative pressure times delta V. And so if we're saying that the volume is constant, that means that this change value is equal to zero. Zero times anything is zero, which means that our work cancels out. So when we're measuring the energy at constant volume, in particular in these bomb calorimetry setups, the amount of energy that's in a system is directly and only equal to the heat of the system. We're not going to worry about that work portion. Now, in practice, it's nearly impossible to observe the temperature changes of the individual chemicals or the molecules involved in the reaction. So instead, what we do is we monitor the temperature change of the surrounding area and use that to infer what happened in the system. So again, the system is the thing that we're studying. The surroundings is everything outside of it. So what we're going to do is we're going to place a thermometer in this insulated environment and see what happens in the surrounding. Whatever happens in the surrounding is going to be equal but opposite to what happened in the system or the reaction itself. Okay. And so in this particular case, the surrounding that we're going to be using is the bomb calorimeter. And it's the sealed insulated container that's filled with water. And so if we can measure the amount of heat or the temperature change in the surroundings, the system or the reaction is going to be the same number, but opposite, equal but opposite. What I gained, you lost, or vice versa. And so we can come up with this scenario that the heat of the surroundings is equal to, but opposite, that of the heat of the reaction or that of the system. So this is just a picture representation of what a bomb calorimeter looks like. And this is how we go about measuring delta E, or the internal energy at constant volume. So again, you have your reaction that's taking place in this reaction vessel, but we can't put a thermometer in there to figure out what's happening at that molecular level. So we instead put the thermometer in the external area and measure the temperature change. So if the temperature goes up in the surroundings, well, that means that the reaction had to release some energy to the surroundings. And so from the system, the reaction standpoint, we would say those are negative values. However, if the temperature went down, let's say the temperature in the surrounding decreased, well, that means it got colder in the surrounding areas, which means that heat is going into the reaction, which would mean that you have a positive value for the system. And so we can measure and monitor these energy changes in these calorimeters because we also have awareness of what's called the calorimeter constant, or the heat capacity of the calorimeter, the amount of energy per degree Celsius that it can obtain before we see a change. So again, we're going to be measuring what's happening in the surroundings and using that to infer what's happening in the system. So it says here, when 1 mole of sugar is burned in a bomb calorimeter, the temperature rises from 24.92 degrees Celsius to 28.33 degrees Celsius. If the C-cal, the heat capacity of the calorimeter, is 4.9 times 4.9 kilojoules per degree Celsius, find the energy for burning 1 mole. Okay. And so 1 mole, we're just dealing with basic sugar here. And so it's, we started with 1.010 grams of that sugar, and it's being placed in this calorimeter. And so with these problems here, what we like to do is, again, we're going to figure out information about the calorimeter itself. We have enough information to figure out how much heat is either being absorbed or lost by the calorimeter. The calorimeter represents our surroundings. So we could say that the calorimeter's heat is equal to the C-cal, the heat capacity of the calorimeter, times delta T. Well, C-cal in this case is 4.90 kilojoules per degree Celsius. And delta T, we would take our final, which is 28.33 minus the initial 24.92 degrees Celsius. Okay, and so if we plug that in, we have 28.33 minus 24.92, and that gets us 3.41 degrees Celsius change. And we're going to multiply that by 4.90, and we end up with 16.7 kilojoules, because our Celsius unit would cancel out. So what this means is inside the calorimeter, we gained 16.7 kilojoules of heat. So what does that mean in terms of the reaction or the system? Well, the Qcal is equal but opposite to that of the reaction or the system. So therefore, the reaction, the heat of the reaction, would then be equal to negative 16.7 kilojoules. The reaction lost that amount of heat, and the surroundings, the calorimeter, gained that amount of heat. And so then we have to go remember that the heat of the reaction is equal to the energy of the reaction in these bomb calorimeter situations. And then the last thing it's asking us for is to figure out the amount of energy associated with this type of process per 1 mole of substance. So we have the gram amount of substance, 1.010 grams of C12H22O11. Well, we can very easily figure out how many moles that is by adding up the molar masses. So we'd have 12.01 times 12 plus 1.01 times 22 plus 16 times 11, and that's going to give us 342.34 grams is to 1 mole. So to figure out how many moles we have present, we would take 1.01 divided by 342.34, and that's going to get us 0.00295 moles. And so to figure out the energy, the delta energy of the reaction per mole, we would say 16.7 kilojoules divided by the 0.00295 moles. So when we plug that in, divided by 0.00295, we end up with a value of negative 5.66 times 10 to the third kilojoules per mole. And that makes sense because, again, we know that our reaction has lost some heat. The heat went where? Into the calorimeter. And as a result, the temperature in the calorimeter went up. Okay, so use all that kind of conceptual knowledge to make sure that your answers are making sense. All right. So this one says when 1.22 grams of a sample is burned in a bomb calorimeter, the temperature rises from 20.27 degrees Celsius to 22.67 degrees Celsius. If the change in energy for the reaction is negative 3.23 times 10 to the third kilojoules per mole, what is the heat capacity of the calorimeter? So in this case here, we're starting with information about the reaction, and we want to figure out what's happening in the surroundings, the calorimeter itself. And so us knowing that the energy is equal to negative 3.23 times 10 to the third kilojoules per mole. Well, if we wanted to think about this in terms of the heat of just the reaction, we got to get rid of those moles. And so the first way we can do that is to say, okay, well, I have 1.22 grams of this substance, and it has a molar mass of 122.112 grams is to 1 mole. And so we can plug that in and get 1.22 divided by 122.12, and that gives us a mole amount of 0.00999 moles. So to get this just to the heat of reaction, we would take negative 3.23 times 10 to the third kilojoules per mole, and we're going to multiply that by 0.00999 moles. So take that times negative 3.23 e to the third, and we end up with negative 32.26 or 0.3 kilojoules. So that is equal to the heat of the reaction. That's how much heat the reaction, in this case, if it's negative, lost. So if that's the heat of the reaction, that means that the heat of the calorimeter would be opposite of that, positive. So it'd be 32.3 kilojoules. Well, now if we know the heat of the calorimeter, we can now say that, well, the heat of the calorimeter is equal to the heat capacity of the calorimeter times the change in temperature, and rearrange and solve for Ccal. Ccal would equal the heat of the calorimeter divided by the change in temperature. So that would be equal to the value we just calculated, 32.3 kilojoules, divided by the change in temperature, which we know that the final is 22.67 minus the initial of 20.27. And so that'll give us 32.3 divided by 22.67 minus 20.27. I'm just placing that in parentheses. And what I end up getting is 13.4 kilojoules per degrees Celsius, because these are Celsiuses. And that would represent the heat capacity of that object, that calorimeter. I hope this information helped you understand bomb calorimeters and how to do the calculations associated with them. Make sure you guys like, comment, and subscribe, and let me know other content that you would like to see. Come back for later videos where I'll be discussing more energy-related concepts in future ones. Have a great day. Talk to you guys soon. Bye-bye.